If we look at this chart, one thing that you might not have noticed is on the periodic table, scientists have come up with and identified and or created up through element 109. This one stops just past 80 right here. It does not go on. It's not truncated and there's something continuing. That's it. So what that means is there's a finite number of elements that exist as stable isotopes. It turns out that element 83 is the last largest stable isotope. What that means is anything larger than 83, so 84 through 109, all of those isotopes are only radioactive. They don't have any stable isotopes. They're all unstable. They're unstable because they're so large. We can somewhat say that the nucleus is too large. So in order to try and become more stable, what the nucleus in some cases tries to do is kick out a big chunk of the nucleus. And a big chunk of the nucleus translates to an alpha particle. An alpha particle is the same as a helium nucleus. So it has 4 particles, 2 protons, 2 neutrons. And so this nucleus is really trying to shave its size down by throwing out big chunks. If we take a look at an element that goes through alpha decay, radium is a good example. And we'll look at radium-226. Radium is element 88. So it's going to kick out an alpha particle. And the way we represent that is helium, and it has a mass of 4, 2 neutrons plus 2 protons. It has a charge of 2 from its 2 protons. Again, we're going to always get gamma radiation in our nuclear decay. So now I have to have something plus 4 that gives me 226. So the mass of my new isotope is going to be 222, and the atomic number of my isotope is going to be 2 smaller than radium. So we have element 86. Element 86 is radon. So when we go through alpha decay, generally it's going to be elements that are larger than 83 that go through it. Not all of them do, and they don't just go through alpha decay. Elements above number 83 can also go through beta decay and positron emission or electron capture. And many times what they do is they'll alternate different types of decay as they're trying to reach that stable state. Just because this decay has gone to radon doesn't mean it's going to stop. Radon, also being radioactive, is also going to go through its own pattern of decay. Probably go through at least some alpha decay because, again, it's such a large nucleus. There are 2 other types of nuclear reactions that we'll talk a little bit about. These are not examples of decay. Fission is an example of a man-made nuclear reaction. And in fission, what happens is we are bombarding heavily nucleus, so usually elements with atomic number 90 or higher, and we're bombarding them with a slow neutron. The goal is you want to not hit it like you would to break up pool balls on a pool table to get them to scatter. You are throwing a slow neutron at it so that hopefully the neutron sticks, and then the nucleus just collapses, similar to building a house of cards, and the very last card is just too much and the whole thing collapses. That's the analogy that works better when we're talking about fission. So an example of fission, the most common one is looking at uranium. Uranium-235 is the isotope of choice of uranium going through fission. Uranium's element number 92. So I'm going to add a neutron, mass of 1, charge of 0. So I have to keep track now that my total mass on the left-hand side is 236, not 235. And when fission happens, there are 2 new elements formed, and they are approximately equal in size. They aren't going to necessarily be exactly equal. And what we find is we're usually going to end up getting elements in the 5th or 6th rows of the periodic table. So for this example, what this uranium nucleus is going to decay into is the element strontium, and it's going to decay into strontium with a mass of 90. Strontium is element number 38, and it's going to also decay into xenon. Xenon has a mass, in this case, of 143, and xenon is element number 54. So that's not exactly even, but that's what I meant. It's about. We're not going to have hydrogen coming off and something that's still very radioactive. We also get neutrons, and we may get 1, 2, or 3 neutrons. In this case, we're getting 3 neutrons the way it's working out, plus lots of gamma radiation. If the number of neutrons varies, what that's going to do is that's going to vary one of the isotope numbers. So if I were to have only 2 neutrons, then I would probably end up with xenon as 144. Or if xenon stays 143, then strontium would be 90. If I only had 1 neutron being created, then I would have xenon being 145, or I would have strontium appropriately larger. Remember, my top numbers, my mass numbers, all have to add together to make the 236 for this reaction that starts on the left. The other type of nuclear reaction is fusion, and people have been trying to get fusion reactions to go for many years. The advantage of fusion is you get lots of energy and you do not get any radioactive particles being created. So you create stable isotopes, not radioactive isotopes. The problem is you need huge amounts of energy to get it going. Another way of saying it is you need a really, really big activation energy. Fusion is combining light nuclei, usually starting with hydrogen or helium, and they combine to make a heavier element. We start with hydrogen, that's the smallest thing we have. So we have hydrogen with a mass of 1 and a charge of 1. We're going to take 2 of them, and we're going to end up with, for this particular example, there are a variety of processes that it can go through. We're going to end up with another hydrogen isotope, but this time with a mass of 2 and a charge of 1. So that means that our new particle that we create here has to have a mass of 0 and a charge of 1, so we're creating a positron. Once we get these heavy hydrogens or deuterium isotopes, they are much easier to work with. So if I take 2 deuterium isotopes and combine them, then I'm going to end up with something that has a mass of 4 and a charge of 2, or I get a helium nucleus. And this reaction is what happens in all stars. Our sun is cranking out helium and the appropriate amount of energy constantly, huge amounts. That's where all the elements in the universe come from, are stars going through fusion. And they actually go through a lot of fusion really fast when they go through a supernova or a nova process. So all the elements in the universe have come from stars going through fusion, usually at fairly high rates. One of the concerns, especially in this country, about nuclear power is, what do we do with the waste? How do we safely transport the waste from where it's produced to where it can be stored? And where are we going to store it? And most states have idea of or have expressed a concern that they don't want it stored in their state. One of the ideas is storing nuclear waste in fairly non-reactive form. It's called vitrification, where they heat the waste up to a really high temperature, essentially melt it, and then cool it quickly so it takes on the physical state similar to glass, and it doesn't really react in that form. The storage would be in the bottom of expired coal mines, sulfur mines, salt mines, so that it's deep under the surface of the earth, away from living organisms so that any radiation's there, it's away from other people, and these are empty spaces that aren't being used, so they could conceivably be used to store our nuclear waste because it's going to be around for several more million years. And so that's where Sidney Harris came up with this cartoon. Nuclear radiation is the stuff radiating or being given off by nuclei when they go through change. Alpha radiation, again, as we said, are helium particles. Helium, and what we're going to do is compare these 3 types of nuclear radiation in terms of their size, charge, speed, all that other good stuff. Alpha particles are large, both in mass and in volume. They're also large in charge. They have a +2 charge. And anytime you have a charged particle, what that means is when it comes in contact with molecules that make up living organisms, it can pull electrons off or add electrons to that or ionize those particles. And once the molecules that make you up start ionizing, you kind of fall apart, which is one way that radiation damage occurs when radiation comes in contact with living tissues. Alpha radiation is relatively slow moving, and if you wanted to stop alpha radiation from attacking you, from doing any damage to you, a layer of dead skin will do it. Your clothing, a sheet of paper, all that can stop alpha radiation. 10 meters of air will do about the same thing. Beta radiation, remember beta particles are nuclear electrons, so they're tiny, both in size and mass. They have a smaller charge and it's negative. Because they're charged, they can ionize molecules, biological molecules. Because it's -1 instead of +2, so it's half the size, it won't ionize as much as alpha radiation. They're relatively fast moving, and if you wanted to stop beta radiation, you'd need some relatively thick layers of glass or wood or metal. If you're inside a building, you're essentially protected from beta radiation. Gamma radiation is not a particle. It's pure energy. It has no charge because it has no particle, and it has very high energy. It also moves at the speed of electromagnetic radiation, which we found before is 3.0 times 10 to the 8th meters per second. Because it is so high in energy, it can ionize particles just because the energy is such that it can knock the electrons off. If I want to stop gamma radiation, I need several inches of lead or several feet of concrete and steel.